This is problem 13-71. In this problem, a tow truck is pulling a car up a 25-degree incline using pulleys as shown in the figure below. If the tow truck accelerates at a constant rate of 4 feet per second squared, determine the speed and acceleration of the car 5 seconds after the tow truck starts from rest. Okay, so this tow truck is driving along a flat surface, but it's pulling the car up the incline, and it is connected by this cable, which is then connected to a pulley. The cable is assumed to be unstretchable and indestructible. And so this pulley system is actually going to affect the relative speed of the car relative to the truck. So if you have any general understanding of how pulleys work, you'll know that the string will get pulled by the truck a certain speed, and then the string will be pulled up on this side of the pulley at basically half speed, because half of the distance will be taken away from the bottom string, and then half of the distance will be taken away from the top string. Okay, so this gives you a mechanical advantage. I can, talk with you during office hours about, more detail of how pulleys, the theory of pulleys works. But understand that in this relatively simple, this is probably the most simple pulley that you could set up. The pulley is going to move in half speed. Let's see what the math looks like for that. Okay, so as far as the truck is concerned, we're given an acceleration. So let's go with the acceleration of the truck is equal to the 4 feet per second squared. This truck is moving to the right. So if I was to just draw a box that represents the truck, we know that the truck is going to be moving to the right, and then the car is going to be on an incline, and that is also going to be moving to the right, but there is going to be a 25-degree angle. Okay, so we're given the acceleration, and we're also told that the initial velocity of the truck is equal to 0 feet per second, because it does say that the truck starts from rest. All right, they give us some other information that 5 seconds after the tow truck starts from rest. So we know that the final time that we care about is going to be it's going to be 5 seconds. All right, now let's just go ahead and do what we've done. Let's integrate and let's get the velocity of the truck. So like I said, this is the initial velocity of the truck, and this is the acceleration as a function of time. So now let's get the velocity as a function of time. So that'll be the integral of the 4 feet per second squared. So that'll be 4t, and then plus c, like we've done before, but the initial velocity is 0. So therefore, the velocity as a function of time of the truck is 4t. Okay, now we have to figure out how the car is going to move relative to the truck. We have to use the pulley. We have to use what we know about the pulley. So let me draw the pulley a little more correctly. So let's have the small pulley here, and then it's anchored to that larger spool, okay? So what's going on is you'll have a length that equals the pulley, and you have a length here that is however long the truck's cable is, and then this pulley will basically have a length also, and that we can call that the length of the car. So distances in this book for problems like this, the book uses S. All right, sometimes you'll use X, sometimes you use Y, for displacement, sometimes you'll use D. Right, so in this case, they use S a lot of times, and what we want is we want the entire length of the pulley's cable, and then we want to reference that to how long the truck's cable is and the car's cable is at any particular time. Why? Because this small pulley will move forward as this cable is pulled by the truck a longer distance. So what'll happen later on, and I'll use a different color, later on, the length of the truck, so I can call this like S truck prime, will get longer, and the pulley will get closer, and so the length of the cable that's related to the car will get shorter. So this will be like S prime C. So the lengths of the cables will change for what the car is connected to and what the truck is connected to, but the total length of the cable doesn't change. All right, so what does that mean mathematically? That means there's a length of the cable. I'm going to represent that as L. That's going to be equal to the sum of however long the truck part of the cable is plus however long the car cable is. But the car cable is happening twice. There is, if we go back to the original, there is a top cable and a bottom cable that are related to the cable that's on the car side of the pulley. All right, so that means we have to put a 2 here. All right, so this is basically our distance equation for how far away the car is to the top of the hill and how far away the truck is from the top of the incline. All right, and they add up. They always add up to the length of the pulley. So that's what I'm doing. I hope that's making sense. All right, now what do we do with this? If we derive now, this is a distance equation. If we derive into velocity and then derive into acceleration, we get equations that are velocities that are based on distance. Okay, this might be a little confusing. And also, let me do the math on that. So the derivative of the length is always the whole cable. The cable doesn't stretch. There isn't new cable added. We don't trim the cable. So this L is a constant. If you take the derivative of a constant, you end up with 0. So understand, I'm taking a derivative on this step. So this is going to be the derivative. All right, and then I'm simply going to take the derivative of f sub t by just putting a dot. All right, this may seem kind of weird and kind of a cheat, but it's totally allowed. And then 2SC this is a dot as well. So I asked you at the beginning of the semester what do these dots represent? And the dots represent the velocities, or actually the derivatives of functions. All right, so ST and SC can change value. So they are functions, and the dots on top are just the derivatives. We can take the derivative again. Okay, so we'll say this is derivative 2. And so there is 0, 0. Derivative of S sub t dot is S sub t double dot. And then the derivative of 2S sub c dot is S sub c double dot. So this is an acceleration. And this equation here is a velocity. All right. Now, we were told that we care about time equal to 5 seconds. All right. So that means that we can find some sort of information about the velocity. If we know the velocity of the truck is 4t, and we know we care about 5 seconds, that means that the velocity of the truck at 5 seconds is going to be equal to 4 times 5 seconds, which is 20 feet per second. Okay, hope you're following that. But we also know that the length of the truck's cable is also the distance that the truck is from the main spool, this spool over here on the right. Okay, and the derivative of that distance is going to be the truck's velocity. So 20 feet per second is equal to S sub t dot, because that is what S sub t dot is. Okay, now S sub t double dot, we already know, is the acceleration, so 4. All right, well now we can learn some stuff about the car, because we know that 0 is equal to S sub t dot plus 2S sub c dot. And since we know what S sub t dot is, it's 20. That means that we can substitute and we can find the velocity of the car, right? And that adds up to the velocity of the car equal to negative 10 feet per second. Okay, because it's just 20 subtracted over and divided by 2. Right? And then the velocity, sorry, the acceleration of the car is going to be equal to what we find for this equation. And we know that 2s sub c plus double dot plus s sub t, the acceleration of the truck, okay, s sub c double dot is equal to 0, and s sub c double dot is equal to 4. So that means we can subtract the 4 over, and s sub c double dot is equal to negative 2 meters per second squared. And that's the answer. The car's speed at 5 seconds is negative 10 feet per second, okay? And the car's acceleration at time 5 is negative 2. Now, negative, wait, I thought that the truck was moving to the right and the car should be moving to the right as well. Well, okay, yeah, but the negative is slightly misleading. And you do have to kind of know that since the car is on an incline, it's not even really moving horizontal in the first place either. So you have to take into consideration some, I hate to use this word in engineering, but some common sense knowledge. You have to connect the diagram to the numbers and try to understand that this negative value that you're getting is a bit misleading because this car isn't even actually running along a flat plane anyway. We've rotated the axes. You'll get more practice with this kind of thing in future problems. So I'm gonna unfortunately kind of say, just kind of go with it on this one, and we'll get some more opportunities to see this kind of thing in action later.